All right, so let's talk about equations of motion. All right, so our equation of motion, our EOM, for the rest of the semester, is an equation that provides the basis for modeling our vibrating systems, right? About its equilibrium point. So the important thing is that an equation of motion is about an equilibrium point. And for the homework, for the example we did, right, that's why we have to solve for our delta deflection, because we have to find that equilibrium point. Does that make sense? So, and it's a transfer of potential energy from the spring to the kinetic energy of the mass. You always have the same amount of energy, I mean, at least if you don't have a damper, and it's just going to kind of sit there and vibrate forever. So to develop our equation of motion, let's assume that our systems are frictionless like we did before, and that we're not pulling any energy out of the system. So let's go ahead and draw our buddy here. K, mass, positive to the right. And the sum of right, so now we want a free body diagram of this. So we've got a force on our mass. If we move to the right, like X is telling us, the force is acting to the left, correct? That make sense? So the force is acting to the left because we moved to the right. You're more than welcome to define it the other way. The equation of motion should come out the same. Right? And then we have a point acting down, and what's this force going to be? Yep, mg. And then we have a normal force acting back up, right? Newton's third law. So that gives us our equation of motion. So, well, so that doesn't give us our equation of motion. That, well, oh no. Okay. All right, so we're interested in our forces in the x direction, right? Let me make sure I get this right. So we only have one force in our x direction, so we have to, when we start to move this, right, that has to equal to our force, which is our mass times acceleration, right? So again, the acceleration of the mass, the sum of forces in the x-axis must equal the mass m times the acceleration of the mass. And that's ax dot. That makes sense? I mean, that's literally all we have to work with, right? So if we consider that the positive displacements are to the right again, so the standard form of the equation of motion for an on-damped system is S1 x double dot, which is our acceleration, plus S2 x is equal to 0, right? Mathematically, that's what we have to have happen, right? So we're just changing our energy that's associated with our acceleration with our energy that's associated with our displacement, right? And which is mass and stiffness, and we'll get there. So our S1 and S2 are constants that need to be determined, and we can determine those from the free body diagram. So just like on your homework, right, you've got 3 steps. Also on your homework, if you can, just do the homework on the paper provided, and 1 problem per page. That'll make life easier for you when we do the self-assessment, right? So if you cram everything onto 1 page and you have to redo a problem, that becomes a problem. Like if you cram 4 problems onto 1 page and you have to redo problem 3, then it just looks odd. So just do 1 problem on a page. And then preferably use the paper that was handed out, but that's not the end of the world. So you've got 3 steps. For building an equation of motion, right? And these are literally laid out for you on the homework. So step 1 is draw a free body diagram at the system's equilibrium. And displaced position, right, without the displacing force. And again, that's kind of what we talked about before, right? When we talk about our displaced position, we pull it a little bit to the right and we release it on that example we talked about. That's how I think about it. You know, it's the displaced position without the displacing force. But if you want to think about it in like a mechanical sense, if you pull something and then you release it, the instant you release it, that's the image we want to draw. Right, so step 2 is apply Newton's second law to both equations of motion. And step 3 is to combine the equations to write the equation of motion. So there's lots of canceling, as you've seen through the homework, I hope. Combine the equations to write the equation of motion in standard form, right? So in standard form, forcing is on the right-hand side, but does any of the homework or any of the examples we've looked at so far have any force applied to them? Right, so that's just going to equal 0, right? So your right-hand side of your equation of motion is a 0. So if we do that for this system, we get mx double dot plus kx equals 0. And again, that 0 is our forcing function. That make sense? Yeah, go ahead.
Professor, you just said that you don't have a force that is applied, so your equation of motion will equal to 0. However, what would cause the system to have a displacement if there's no force and it's at equilibrium?
Yeah, so, yeah, words are tricky. We don't have enough words. When we talk about a forcing function, that's something that's constantly applying force, right? Like maybe you have a motor hooked up to a shaker, and the motor is constantly applying force. Here we're interested in free vibrations, where you have a displacing force and you let go, and then you're done. and you don't touch it anymore, right? And so if you have think about it, let's just kind of draw one out. So we are interested in free vibration. Right? So if it's at rest, it's going to stay at rest, which is great, but not very useful for defining anything mathematical, right? So mathematically, a system at rest is pointless. So let's go ahead and draw what we think we're interested in here. So let's go with time and displacement. And so if we have a free vibration, right, we're going to displace it a little bit. So let's start at the top. And then we're going to oscillate forever, right? Does that make sense? Okay, so what does this look like if we put a damper in? Yeah, it's gonna decay exponentially. So maybe something like that. So this is damped and undamped.